Generative AI is a revolutionary general-purpose tool, yet across the modern workplace, professionals are hitting a wall. They deploy these systems expecting massive efficiency, only to receive unpredictable results that require more time to fix than they save. When a model hallucinates a fact or produces a bizarre output, the instinct is to blame the software. We assume the system simply isn't capable enough yet, and that we must wait for the next major update. But the primary bottleneck to your productivity is no longer the underlying capability of the language model. The actual limitation is the absence of operational skill. We are applying a highly advanced tool without a systematic methodology to govern it. Achieving professional-grade reliability requires moving away from casual experimentation and toward a rigorous system of technical management. Immense productivity gains do not emerge automatically from the machine. They are entirely dependent on the human's operational framework. Your skill in managing the AI is the ultimate differentiator in leveraging its power. Professionals must stop acting as passive AI users and move into the role of active AI operators. The passive workflow is defined by hope. Users type unstructured questions into a text box, hit enter, and accept whatever output the system generates, lacking any structural process to audit or improve it. The active operator, by contrast, relies on a disciplined framework. They actively constrain the AI's boundaries, applying specific rules to engineer reliable results. This operational skill set is called AI fluency. It is a mandatory professional competency, mirroring the necessity of basic computer literacy during the early internet era. Developing AI fluency is the foundational requirement for turning an unpredictable black box tool into a controllable professional-grade asset. To build that framework, we have to look under the hood at how generative AI systems actually construct their responses. Generative AI relies exclusively on probabilistic next token prediction. It calculates rather than thinks. Scanning massive patterns from training data, the system mathematically calculates which word is most likely to follow. This leads to the defining maxim: they are predictive, not cognitive. AI models possess zero inherent reasoning abilities. They cannot apply logic to a problem. They also possess absolutely no true understanding of the domain they are generating text about. They process text as mathematical tokens, not as human concepts. Because every output is purely the result of mathematical probabilities, accuracy is never guaranteed by the system itself. This chart shows the resulting spectrum of AI outputs. Every generation lands somewhere on this sliding scale, from useful to misleading to completely incorrect. On the useful end of the spectrum, the statistical patterns the AI identifies happen to align with factual reality. On the incorrect end, those same pattern-matching algorithms generate information that reads as highly plausible but is entirely false. AI hallucinations are not software glitches. They are the natural result of an unconstrained probability engine doing exactly what it was programmed to do: guess the next word. The AI cannot apply independent logic to verify its own work. Therefore, the human operator must intervene, providing the rigid constraints that force the probability engine into the useful zone. The first pillar of the 4D operational framework designed to constrain that probability is delegation. In the AI era, delegation requires the analytical skill of rigorous task design, going far beyond the traditional act of handing off a project to a colleague. Select tasks that perfectly fit the AI's pattern-matching strengths, like repetitive work, drafting content, and summarization. Conversely, assigning high-stakes decisions, ambiguous goals, or tasks requiring deep domain certainty guarantees failure. The primary operational tactic here is to dissect complex projects at the planning stage, cleanly separating them into AI-suitable tasks and human-required tasks. Proper delegation acts as the crucial first filter. It actively prevents the operator from asking the system to calculate probabilities for conceptual tasks it is inherently incapable of understanding. Once a task is properly selected, we move to the second pillar of the framework: description, commonly known as prompt engineering. Description serves as the primary mechanism for setting strict mathematical boundaries on the AI's probability engine, replacing the standard conversational approach. This requires extreme clarity and direct instructions. You must eliminate any vague guesswork from the input. However, you must also avoid overly complex or convoluted instructions, which can confuse the system's pattern matching process and degrade the output. The operator must define the exact output requirements before generation begins, explicitly stating what the final product should look like. A reliable tactic is imposing rigid structure. Request specific formats, such as bulleted lists, using structured tags, or defined sections. A more advanced technique is providing specific examples of the desired result directly within the prompt itself. These examples act as heavy statistical anchors, pulling the model's probabilistic output firmly toward a highly specific pattern. Precise description strips away the model's freedom to hallucinate. It forcefully engineers the system to generate text strictly within your designated parameters. After generation, a massive organizational risk emerges, overtrusting confident, authoritative-sounding AI outputs. An output can look polished on the surface while hiding deep structural flaws. This introduces the third pillar, discernment. This is the essential human quality control skill required to evaluate the output. Applying discernment means relentlessly cross-checking accuracy, completeness, and relevance against your own domain knowledge. It is the only firewall capable of preventing probabilistic errors from permanently contaminating high-stakes professional workflows. Even with exceptional task selection and precise prompts, first-attempt AI outputs are rarely perfect. This necessitates the final pillar, diligence. This is the execution discipline required to iterate on your initial work and refine your instructions. These 4 pillars merge into a continuous operational loop. A task flows sequentially. You describe the prompt, evaluate via discernment, and use diligence to route findings back, physically adjusting the description block. High-quality professional results are born exclusively from this iteration process. They almost never come from a single perfect prompt. Embracing this continuous loop is the mathematical guarantee that shifts a user's experience from unpredictable noise to refined, reliable automation. This 4D continuous loop fits into a larger automated workflow model. Scaling this process requires mapping these steps into a rigorous sequence. Begin with highly simple loops and iterate forward, gradually expanding the framework across multiple parallel workflows. Adding structure to these prompts steadily improves the baseline quality of outputs across the board. Through diligent iteration, you eventually yield highly reliable, locked-in prompts. These optimized instructions constrain the AI so effectively they require significantly less manual discernment over time. Once these hardened, reusable prompts are established, they can be deployed at massive scale to automate complex workflows safely. Mastering the single operational 4D loop is the absolute prerequisite to safely scaling AI capabilities across entire organizational systems. Relying on a non-cognitive system to simply figure it out guarantees failure and frustration. The machine requires strict human governance to function properly. The definitive mandate of the active operator is to mathematically engineer reliability. Achieve this by designing tasks, aggressively bounding input variables, and uncompromisingly validating output data. By mastering the AI Fluency framework, professionals navigate the volatility of probability. This systematic approach constrains the algorithm, providing the predictability required for professional scale work.